Hello and welcome everyone. I made far too many videos about no contact cube actions, and this is not one of them. Or maybe it is. Here's the deal. I routinely remind viewers that race formulas are designed for money play, that is, unlimited cube, so less useful in matches when the score gets unbalanced. But dice be dice, and sometimes you find yourself ahead or behind by a lot. What then? Maybe we can bypass the issue by conjuring a formula for estimating CPW, the cubeless win percentage, and combine it with match equities to figure out cube actions at any score. Sounds great, you say, but I find the idea unfeasible. And I'll explain why by showing you what I found when I tried to construct such a formula. Some of you are rolling their eyes and saying, Pepe, we already have it. It's called the Klineman Count. Look it up. Yes, I'm familiar with it. Only I call it the Klineman transformation, because it's based only on pip counts, which existed long before this transformation. But you're correct in one thing. It's a great place to start. We routinely use the pip count difference to assess the race. There's even a handy method for computing the pip difference without needing to count each side separately. Sadly, pip difference by itself is too weak. You might have seen this figure or something similar already. Here, each point represents one no-contact position. The x-axis is the position pip count difference, and the y-axis is the CPW. Strong correlation, obviously, but a poor predictor. For differences between 0 and 10, you can find positions with any CPW you desire. Here's some examples for 5 behind. CPW can be 1%, 30, 50, 70, 90, or anything you wish in between. And those are from my test suite, positions from actual play, not anomalies constructed to make a point. So Klineman does not use the pip count difference. It uses both counts, which contain information not only about the size of the lead, that's the pip difference, but also on the expected number of rolls until the end of the game. Here's one example. First, subtract 4 from X count, the player on roll. This offsets the fact that he is a roll ahead. Now, compute D, the difference, and S, the sum. Divide D squared by S to get K, 1.33 in this case. Now, take the square root of K, divide by -2, and compute the complementary Gauss error function, ERFC. Then divide by 2. Voila! 79.2%. 7% away from the true value. I think this example illustrates nicely why people talk about Klineman, but no one uses it. It's mentally exhausting. Squaring, floating point division, square root, and the impossible to compute ERFC. I obviously exaggerated, because no one does square roots or can compute ERFC. The suggested practice is to memorize key values and interpolate between them. Even so, good luck convincing people to go through this computation reliably while the clock is running. Worse, let's ignore all that and examine how good it is. These figures show the Klineman CPW estimate versus true CPW. It's concentrated around the truth, the yellow line, but arbitrary large errors abound. The average norm 2 error, based on 1.8 million positions taken from my test suite, is 11.4%. So 7% off is actually quite good for Klineman. To summarize, Klineman is extremely demanding over the board and far from accurate. I apologize for sounding harsh. I have nothing against the Klineman transformation. It's just one method among others. But I am annoyed by people who most likely never used it and yet glorify it to sound smart. And I would be saying that even if I had nothing better to offer. I do. But mind you, while it's better, it's not good enough to be useful. And what do I offer? There are two obvious ways to approach the problem. The first is to take the adjusted count of any race method and map it into a probability. Let's take K-star, the modified Keith count, the best catch-all method I know of, and map its modified count to the mean CPW of all race positions having this count. This is how it looks. For our sole example, the K-star count is -4, which maps to 64.4%, so slightly worse than Klineman, 8 versus 7%. Which sadly sums up this attempt. You need to remember key values and interpolate, just like Klineman, and even if you manage it, the overall mean error is 12.4, slightly worse than Klineman. Instead, here's something simple you can compute over the board, K star P. Divide the space into bare-off and non-bare-off, and use these two simple formulas, 74 plus 3 times the K star count for bare-off, and 78 plus twice the count for race. K star P gives 70% in our example. Overall, the mean error for bare-off positions is 12.7% and 6.6% for race, and since race positions make 35% of the space, the overall error is 10.9%. So, there's very little to remember, 78.2 and 74.3. Computing K star P is easy online and manageable over the board, and overall, it's more accurate than Klineman. But there's a better way. Go back to basics and derive a formula from the same ingredients used by race formulas. Here's RAX1, race, checkers, crossovers, and 1 point. And sorry about the terrible name. 62 minus twice delta race, minus 6 times delta checkers remaining, minus 1.5 delta crossovers, minus 1.5 delta checkers on the 1 point. Looks a little scary this way, but those are just the familiar building blocks of good old Thorpe. Delta race is the pip count difference, delta checkers is the difference in number of checkers for each side, delta crossovers, the difference in crossovers, and delta 1 point is the difference in checkers on the respective 1 points. Here, delta race is -9, white is 9 pips ahead, 15 checkers each, 2 crossovers each, so 0 and 0, and white has 1 extra checker on the 1 point. So 62 plus 18 minus 1.5, 78.5. This formula has mean error of 8.8%, and again, we can do better by splitting to bare-off and non-bare-off. In race, use 60, 2, 2.5, 2 and 2. So actually remember 60, 2.5 for checkers, and 2 for the rest. And for bare-off, use 65, 2.5, 6.5 and 2, because there's no crossovers. Splitting buys another 0.5%, so total error down to 8.3. Let's illustrate with 2 examples. Here, pip difference is 15. White has 1 checker off, so +1 for black, and black also has 4 crossovers and 2 checkers on his 1 point for his troubles. 60 minus 30, that's 30, minus 2.5, 27.5, minus 12, 15.5, 1% off. And this is bare-off. White is 6 pips behind, ahead by 2 checkers on the board, and 2 on the 1 point. 65 minus 2.5 times 6, that's 65 minus 15, 50, plus 13, plus 4, 67, 2.5% off. I'm rushing through a lot, I know, but in my defense, it's not a tutorial and not live. You can pause, rewind, and take screenshots. Moreover, it's not something anyone going to use. I'm making a point, or an anti-point actually, on why I think this direction is a dead end. I might be wrong. Perhaps the Mochis and Michis of the world have a secret formula up their sleeves to squeeze a few millipoints from us mortals. But until such wonders see the light of day, this is, in my opinion, the state of the art of something normal people can use while playing. And I can't see how RAX1 or K-star P might be useful tools, especially as I expect advanced players to be able to match this accuracy for positions of interest. And speaking of interest, are you interested in testing yourself on this topic? Let me know, and if there's enough interest, I might cobble up a page. Until then, adio.